Hello and welcome to the complete marking scheme of the KCSE Physics Paper 1 of the year 2021. Complete marking scheme of the KCSE Physics Paper 1 of the year 2021. I've prepared this marking scheme with the aim of showing you how the answers were arrived at. And in order to make your study a little bit more comfortable, I have provided you a package in the video description. If you download it, you'll be able to have what I have here. I'm using my web browser to view this particular package, and you will too be able to do that if you download that folder into your computer. Double click the folder, and once you're inside the folder, you will find, let me just take you through this so that you can be able to see what I'm talking about. So I'm going to put away that one and get this folder. Once you have downloaded it, you will see a folder named KCSE Physics Paper 1 2021 package. Double click it. Inside there, you're going to get very many files. Scroll down until you come to a file named index. You'll find that it will have an icon showing you the application you can use to open that file. It's a web browser. So if you're using Chrome, it will have the icon of the web browser Chrome. If you're using Microsoft Edge, it will show Microsoft Edge. Whatever browser you are using, it will show that particular browser. But I will suggest that you use Chrome because it is Chrome that I've used to prepare this package. So the moment you double click it, you're going to have what I am seeing here. So, and it will read quite clearly, KCSE Physics Paper 1 2021. On the left hand side, you will have a neat navigation showing you the menu of the KCSE Physics Paper 1 2021. There is a video solution of what I'm going to talk about in the whole of this lecture. There is a video solution. I'm going to click it to show you how it works. There is section A of that particular paper. If you click it, you will see the questions which are in section A, and for each section I've taken time to tell you the topic from which that question comes from. For example, question 1 is derived from measurement 2, which is a topic in form 2. If you click on it, right on the right hand side, you're going to have the actual question, and there will be the question itself, the topic from which it comes from, and the form. And then you can attempt the question. One more thing that I'd like you to do in the course of this video: the moment I show you the question, it's always good to pause the video, attempt the question, because you want to do some effective revision. Attempt the question before you check the answer. Where is the answer found? Just scroll down, and a short distance from there you will see, click here to see the answer. It's clearly written there. So don't just rush there and click it, because I want your mind to be searching for something when you're watching, when I'm explaining how the answer is arrived at, because this is how we do effective study. You always study effectively if your mind is looking for something. So I'd like you to not to watch this video like you would watch a movie. I'd like you to be pausing the video, attempting the questions, or when I prompt you to pause the video and attempt the question, please do that, because I want your mind to be searching for something. Once you've got the answer, you will come here, you will click that, and an answer will pop up just like that, and you can be able to mark your work. This is the best method of revision. So let me go to the video section, or the video solution to the whole of this paper. If you click on it like that, a video will pop up. But you can see for me, no video has popped up here because I'm offline. So let me go online so that I can be able to show you what happens. So my internet is now connected. Let me refresh the page. We see what is going to happen. And there we have it. I'm using a different paper because the video that you will see is the video that I'm going to be talking about now. So I've just taken one of my videos that I've prepared recently, but the thing I want to show you is that the moment you can be able to play that video on this particular page, instead of going to YouTube, you will play it on this page. And let's just do that and see what we get. And the rare functions, of course, it is sound wave, and when two sounds meet, and you can see it is playing. Let me pause so that I can show you some things. Let me put this one away. If you look at the playback scroll bar here, it is split into smaller sections. Those are called timestamps. I've put timestamps on my video to show you the question. When you want to skip to a particular question, all you need to do is just run your cursor along the playback scroll bar like that, and the question will pop up. For example, when the cursor is there, it is showing me this is question 13 and it is on optical fiber. So if that is the question you wanted to look at, you'll just click at that particular point. Let me click on another question here, EMF and terminal potential. If you just click there, you find that the video straight away jumps to that section and it starts talking about that particular concept. Why is this important? This is important because this video is very long. The video that I'm going to prepare now will be equally long. For example, this video, I just prepared it about a few days ago, and it is 1 hour 45 minutes. It is very long. And if you're not careful, you will not get whatever I'll be talking about there. That is why there are these two things. I'd like you to be pausing the video and attempting the question before I show you what the answer is. That is important because it will give your mind something to think about. And that is when you get the best result when you're watching a video. When you're looking for something, you really do concentrate so that when I mention it, you get it. The other thing is, I have given you an opportunity to jump to the question of your choice. Let's say you have seen this paper before, Physics, Paper 1, the KCSE Physics Paper 1 of the year 2021. Maybe you have seen it before, and it's only particular questions that were a bit of a problem to you. So I've given you the opportunity to skip to that question, see how it is solved, and then you can go on with the rest of your revision. Although in the beginning, I'd like you to play the whole video so that you get the idea of how I'm approaching these questions. You may know the answer to a particular question, but in my explanation, I'll give you extra information trying to test or trying to prepare you on other concepts in the same topic. So that is how I'd like you to treat this material. So let's put this one away and go straight to section A. So let's go to section A of that paper. Of course, there is section A, there is also section B, and we go to the first question. This first question is on measurement 2, and in measurement 2 we deal with just the three things: the vernier calipers, the micrometer screw gauge, and the oil drop experiment. Here they are testing to see whether we can be able to, this time not to read the scale of a micrometer screw gauge, but to try and draw what we would see on the scale if we are given the reading. To draw what once you are given the reading, you're asked to draw. Most of the time we are asked to read the scale when the diagram is given. This time it is to draw when the reading is given. So we have a reading of 3.87 millimeters, and this micrometer screw gauge has 50 divisions on the thimble. That means that the pitch of the micrometer screw gauge is 0.5 millimeters. What that means further is that when the thimble rotates once, the edge of the thimble moves along the sleeve through a distance equal to 0.5 millimeters. So the sleeve is marked in steps of 0.5, 0.5, 0.5. And that is why a reading of 3.87 would like to see to subtract the sleeve scale reading in order to see what will be on the thimble. And remember, we have said the sleeve is marked in steps of 0.5. So we start from 0, we go to 0.5, we go to 1, 1.5, we go to 2, 2.5, 3, 3.5, and then 4. But 4 millimeters is way beyond what we've been given. So this reading lies between 3.5, which is what we are going to have on the sleeve scale, and 4. So we're going to subtract 3.5 from 3.87. We are going to get 0.37. Of course, that one we have not been asked to show because it is already given to us here. 35, 36, 37. If you multiply 37 by the value of the least count, which is 0.01 millimeters, you get 0.37. That is the one which is added onto the sleeve scale. So we are going to subtract the thimble scale reading from this reading here in order to see what the sleeve scale was giving us. And let me go to that because I want to explain something else about a micrometer screw gauge with 100 divisions. So what we are given here is a reading of 3.87. We are going to subtract the thimble scale reading, which is 0.37, because it was right there, it was given. And I'm going to get 3.50. So 3.5 millimeters is what we must show on the sleeve. So on the sleeve, it starts with 0, then we have 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and now we do not see 4. What we see is the edge of the thimble. And then there is this center line on the sleeve. And then we have now a division on the, this must be the 37 division mark. But the thimble is marked in steps of 0, 5, 10, in steps of 5, 5, 5. So if we count from 0 all the way to 50, we will see that this one will be 36, and then we are going to have 35, 37, 38, 39, 1, 2, 3. We're going to have 36, 37, 38, 39, 40. This is for a micrometer screw gauge with a pitch of 0.5 millimeters. What does that mean? Let's just review the micrometer screw gauge. The micrometer screw gauge, right inside, it can be compared to a bolt and a nut. Let me just try to draw some diagram here. May not be so accurate. You'll bear with me. Now this is the screws. I mean the threads on the bolt. This is the nut. Assume it's something like that. Just assume That is a simple nut. Something like that. What we mean by the pitch is the distance from one thread to the next. This thread here to the next. This is the pitch. And this micrometer screw gauge has got a pitch of 0.5 millimeters. It means that if we put a mark here on the bolt and allow the nut to rotate, we put another mark on the nut. If you rotate the nut so that it makes a complete rotation, whether clockwise or anti-clockwise, this edge of the nut will move to the right or to the left, depending on the direction in which you are rotating the nut. If you rotate the nut clockwise, it will move to the right. If you rotate in the anti-clockwise direction, it will move to the left. Point is, if you rotate it once, and you will know you have rotated it once because this mark will come back in line with this one. You will know that you have rotated it once when this mark comes back there. When that happens, this edge of the nut will move either to the right or to the left through a distance equal to 0.5 of a millimeter. And that is why this sleeve is marked in steps of 0.5. What will happen if we have a micrometer screw gauge with 100 divisions on the thimble? Let me duplicate this slide so that I can be able to show you the changes that we expect. This is what we'll expect. For the same reading, we won't have the 0.5 divisions. They will not be there. If they will not be there, it means that this time the pitch is 1 millimeter. The pitch is not 0.5 millimeters. Now the pitch is 1 millimeter. It means that when the nut rotates once, it will move along the bolt through a distance equal to 1 millimeter. So the sleeve is marked in steps of 1, 1, 1. But we want that micrometer screw gauge to read the same or to give us the same reading, 3.87. So we are going to see if we mark in steps of 1, 1, 1, we can only have 0, 1, 2, 3, because the reading 3.87 lies between 3 and 4. So we are going to subtract 3 from here. And we are going to have 0.87. So the thimble is marked, has got 100 divisions. So the division that is going to coincide with the center line on the sleeve must be the 87th division here. So again, I'm going to erase that. In fact, let me erase that, because what I need here is the 87th division. But again, the marks, they are labeled on the thimble in steps of 5, 5, 5. So if you count from 0, 5, 10, 15, 20, 25, 30, 35, you will find that this 87 will not be labeled on the thimble. What you're going to have is the next number with a 5 to 87, the low one will be 85. So that we can have 86, 87, 88, 89, 90. So this is what we expect to see. Remember, it is the same reading of 3.87 millimeters. And this time it has, remember, this stuff does not apply now. It no longer applies. I've shown you what applies now is here. This one doesn't apply because the nut moves through 1 millimeter. So the same reading, when we have a micrometer screw gauge with 50 divisions, this is how the scale will look like. If it has 100 divisions, this is how the scale will look like. You know, these are different questions which can be set. So this time they've given you a micrometer screw gauge with 50 divisions. Maybe next time they can give you a micrometer screw gauge with 100 divisions, and then they leave the reading to be the same as 3.87. And then we see whether you are able to use that particular knowledge. So this is the extra information that I give on this particular area. So I expect when you revise this topic, you should be able to, first of all, determine the value of the least count on a micrometer screw gauge, be able to read the scale of a micrometer screw gauge, whether it has 50 divisions or 100 divisions. The next thing is to be able to identify the zero error on a micrometer screw gauge, and then be able to get accurate reading using a micrometer screw gauge with a certain zero error. So you will find all that in that topic, measurement part 2. And let's go to the second question. So before we go to the second question, when you're revising using that particular package, you'll just click here to see the answer. Very quickly, click that and you can see what the answer is expected. 1, 2, 3.5. So these are the divisions that you are supposed to show. So let's go to question 2, which is on pressure. This question is on pressure, and we are given a siphon. It is used to empty a tank, and in order to start the siphon, state why it must be full of the liquid. It must be full of the liquid so that this liquid can be pulled down the tube, down the siphon, because of cohesive forces which exist between molecules of the same kind, in this case, which is molecules of the liquid. And the reason why X must be below the level of the liquid in the tank is so as to create a pressure difference, so that the pressure at this point of the tube, this point where my cursor is, which is atmospheric pressure plus this height, must be greater than the pressure at this end of the tube, so that actually the atmospheric pressure can push the liquid out of that pipe. The siphon works because we compare the pressure at this point and the pressure at that point. The pressure at this point is always lower than the pressure at this point because this end X is below this liquid surface. So in order to create that pressure difference, you must ensure that end X of the siphon is below the level of the liquid in the container. So those are the two conditions must be fulfilled. Condition number one is that the siphon or that pipe must be full of the liquid which you are removing from the tank. Condition number 2 is that end X of that tube must be below the surface of the liquid. So in future they can ask you a question like this: state the two conditions must be fulfilled for the water or for the liquid to be drawn out of that tank using the siphon. A and B, they are the two conditions. So again, let's quickly check the answer. For the liquid to be pulled down by cohesive forces, and B, for point X to have lower pressure than the liquid in the tank. In other words, to create a pressure difference between the 2 points. And remember, you can always hide the answer again and then you try the question, especially with some of those very difficult questions where you quickly forget how the method that you have just used. You can always use that method. You click to reveal the answer, and then as soon as you read it, then you click it away so that you can be able to see whether you can be able to follow the same steps. It's not one of the best methods of revising because there you're trying to do some rote learning, but it's a method that can be used when you want to understand materials which you have encountered for the first time, and you really don't have time to dig deep into the reasons as to why the answer is given that way. And let's go to question number 3, which is on gas laws, and this is a Form 3 topic. And it's actually testing Boyle's law. So let's read the question together. As usual, you can always pause the video and get the solution, and then you see how I go about it. Figure 3a, this one here, shows a horizontal tube containing air trapped by a mercury thread of length 5 centimeters. The length of the air column is 7.5 centimeters. The atmospheric pressure is 76 centimeters of mercury. The tube is then turned vertically with its mouth facing down as shown in figure 3b here. You are asked, determine the length of the air column inside here. So this question comes from gas laws, and one of them is Boyle's law. In Boyle's law, temperature is kept constant. So we find that P1 V1 is equals to P2 V2. How do I get the air? First of all, it is this enclosed air here which is being tested, which is under test. Under test, this air here. How do we determine its volume? This tube has got uniform cross-sectional area. Remember that this tube here has got uniform cross-sectional area. So in order to get the volume of a cylinder, we usually multiply the cross-section area by the length. And if the cross-sectional area is uniform, then we find that the volume is proportional to the length. This is what I'm talking about. So over here, we have this tube. Going to, this is a cross-section area A, and it's a cylinder like that. So the volume is equals to the cross-section area times the length. Because this cross-sectional area is constant, we can see that this one is volume is going to be equal to a constant times the length. Anytime we multiply something, a constant, by something, then we can say that that physical quantity is directly proportional to this one here. So the volume is directly proportional to the length. Why is that important? It allows us to represent this volume with the length. So when we say that the volume V1 is equal to L1, which is 7.5 centimeters, we are justified in doing that. How about the pressure? We've got this mercury thread and the tube is horizontal. So the weight of the tube, which acts vertically downwards, does not affect the pressure of this gas. So the pressure of this gas is equal to the pressure of the gas on this other side of the tube, which is atmospheric. So P1 is equal to P atmospheric, and P atmospheric, we've been told that it is 76 centimeters of mercury. Now after that, we invert the tube with the open end at the lowest point. Excuse this poor diagram that I'm drawing here. Now when we do this, the weight of the mercury column will tend to reduce the pressure inside here by moving down, increasing the volume, and that is where the pressure inside here reduces. But at some point it stops. It stops at this level. So if it stops at that level, what this means is that the pressure at this point and the pressure at this point, they are the same. The pressure outside and the pressure at the surface of the mercury level at that point, they are the same. So if the pressure here and the pressure here is the same, and the pressure outside is 76 centimeters of mercury, the pressure inside here is pressure due to the gas plus the pressure due to this mercury level. So this is how we determine the pressure of the gas inside here. We just need to draw a horizontal line here on the lower portion of this mercury, and then we say because this point outside is at the same level with this point inside, then the pressure at this point is equal to the pressure at this point. So, but we know that for the pressure for the particle which is outside the tube, the pressure is 76 centimeters of mercury. How about the pressure inside? Here, it is due to this height, which is 5 centimeters of mercury, 5 centimeters of mercury, and the pressure of the gas. So, P gas, which is actually P2, is going to be equal to, or rather, P gas plus H is equal to 76. But we know H is 5 and this is 76. So the P of the gas is actually 76 minus 5, where we have 71 centimeters of mercury. So that is how we determine P2 of the gas. And our aim is to get this L2, which happens to be equal to V2. This L2, how much is it? So by using P1 V1, which is equals to P2 V2, we are able to get L2 because P1 is 76. Our V1 is 7.5 rather. P2 is 71, and we are meant to work out V2. And by manipulating these values, we can be able to get V2. Now, how about if the tube was turned the other way around? If it won't stand the other way around in such a way that this open end is uppermost while the closed end is on the lower part, then we are going to find that the pressure of the gas inside there will be atmospheric plus 5. It will not be minus 5. Remember, when it is horizontal, pressure is atmospheric. Pressure of the gas inside there is atmospheric. When it is, let's go to the question so that I can use the diagrams on the question to explain that point. When the tube is horizontal, the pressure of the gas is just atmospheric. The length of the mercury column has no effect on it. When the tube is vertical with the closed end uppermost, the pressure of the gas is atmospheric minus the length of the mercury column. If we turn it the other way around in such a way that the closed end was lower while the open end was uppermost, then the pressure of the gas will be atmospheric plus the length of the mercury column. So on one side it is having no effect. Here we are subtracting the length of the mercury column, and lastly we are adding the length of the mercury column. Those are the short notes that you should be able to write down as far as this part is concerned. So let's quickly check the answer, and we find that the answer is supposed to be 8 centimeters. And let's go to question 4. This question 4 is on measurement, part 1, measurement of volume of a liquid. We are told that in a physics experiment, a student filled a burette with water up to a level of, I think there is something missing here, up to a level of 15 milliliters. That is how the question reads, up to a level of 15 milliliters. That 15 milliliters is same as 15 centimeters cubed. So I'm going to correct that on the package that I'm going to give you to download. The student ran out 3 drops of water, each of volume 2 centimeters cubed, from the burette into a beaker. So the total volume of the water which was removed from the burette is actually 6 centimeters cubed. 3 times 2, 6 centimeters cubed. Now, what you need to remember here is that the burette is graduated in such a way that the volumes increase downwards. It's not like a measuring cylinder whereby the graduations or the volumes increase upwards. And therefore, as you go down, the volumes decrease for measuring cylinder or for a beaker. But for a burette, the values increase downwards instead of decreasing. So when we remove water for measuring cylinder, the scale reading is going to reduce. But for a burette, it's going to increase by the same volume that was removed out. So over here, you are simply going to add 6 onto 15 and you get 21 centimeters cubed. Again, you can confirm those answers there. The only trick in this question is for you to be able to recall the way the graduations are done on a burette compared to a measuring cylinder. Question number 4 is on uniform circular motion, and you want to find out, state 2 factors that affect the angular velocity of a body moving in a circular path. Factors that affect a given physical quantity. At this point, I want to describe the idea of independent and dependent variables. In physics, we usually investigate how one variable affects another variable. For instance, if you're carrying out an experiment using this spiral spring, the physical quantities which we can measure of this spiral spring is that we can measure its length when it is like this. We can measure its length when a small force is applied, get the difference between the two lengths, and calculate the extension. We can also measure the amount of force that we are applying to the spring. Now, between the extension and the force applied, which causes the other? Of course, this one is very simple. It is after I apply the force that the extension comes into play. It's not the other way around. And if I apply a large amount of force, there is a big extension. So there is a way the extension is related to the force. Those two physical quantities are the physical quantities I would investigate when I'm carrying out that experiment. I want to investigate how the extension is affected by the force. How? Look at that question. State 2 factors that affect the angular velocity. State 2 factors that affect the extension of a spring. Do you see how similar those two questions are? So it means that angular velocity depends on some other factors, and we are only required to state 2. Just like I would be expected to state the factor which affect the extension of the spring. That factor which is affected by another factor, for example, the extension is affected by the force. The extension is referred to as the dependent variable. Dependent variable. Dependent comes from the word, it depends on something. Dependent variable. The variable which causes the extension, is referred to as the independent variable. Independent variable. So over here, angular velocity is a dependent variable. It depends on something else. So once you understand that, let's see how we get those variables. So over here, we are talking about This is the center of the circular path, and there is a particle which is moving in the circular path like this. And in order to get this is the radius of the circular path, and this radius is going to sweep a certain angular displacement, and the particle is moving from point A to point B in that direction, and it takes time t. How do we calculate the angular velocity? Angular velocity is defined as the rate of change of angular displacement. Theta is the angular displacement, and time is the time it takes to sweep, for the radius to sweep this angular displacement. So already there I've got the two factors. So one of them is the magnitude of the angular displacement. Let's say maybe this is 1 second, for example. Another particle is moving along the same circular path, which means the radius has been kept constant, but it sweeps in the same 1 second, it sweeps a bigger value of theta. So where is omega? By the way, omega is the symbol that we use for angular velocity. Where is the omega largest? It is larger here because in the same amount of time, it sweeps a bigger angle. So we've kept the radius to be the same and the time to be the same. It sweeps a bigger angle. So you can see that theta is definitely one of the factors which affect angular velocity, and you can also see that time is also another factor. If it takes a longer time to sweep the same value of theta, then angular velocity is going to be, now if it takes a longer time, to cover the same angular displacement, then omega will be small. So I hope you do understand this, so that as you study physics, as you revise, you will be able to understand that when we are talking about physical quantities and factors that affect a given physical quantity, it's always good to realize which is the one is the dependent and which one is the independent. For example, in the case of the spring, it will be ridiculous for you to say that the force depends on the extension, instead of saying it is the extension which depends on the force. It is ridiculous to say that the force depends on the extension. You cannot reverse those two. So in physics, you're supposed to, think about what you're saying. It's not just a matter of saying it. And this is one of those fundamental things about physics. Physics helps us to understand our environment, and in order to understand our environment, we must be able to describe our environment. One of the ways in which we can describe our environment is to describe the physical quantities that we find in our environment. Physics comes from the word physical quantities. Physical quantities. The measurement of physical quantities is very central to physics. Now, one of these physical quantities that we would want to describe when an object is moving in a circular path would be angular displacement, radius of the circular path, angular velocity, centripetal force, and so forth. As we describe these factors, they are supposed to make sense. When we describe how a certain physical quantity is affected by other physical quantities, it's supposed to make sense. So that was as a by the way, but it is closely connected to the answer that you would expect here. Angular displacement and time are the factors which affect angular velocity. And let's go to the question number 6, which is force, which is on force, cohesive and adhesive forces. Again, you can read more on this particular chapter in Form 1. I think it is topic number 3, where we talk about force. Figure 4 shows two capillary tubes X and Y of different diameters dipped in mercury. Complete the diagram to show the meniscus of Y. Of course, here is just a matter of recall. You have to recall this. You can't work out this. You have to recall it. So when you have a thin tube and a wider tube dipped into mercury, you'll find that the depression in the thin tube is usually larger than the depression in the wider tube. So you expect to draw, in fact, why don't we just go to the answer here? This curved shape here is somewhere between this level and this other level. And you get your 1 mark from there. So read more on cohesive and adhesive forces. There are so many other questions on cohesive and adhesive forces which can be said. So go to that chapter, read a little bit more on that. Now in question number 7, it is on the topic particulate nature of matter. And this question is on diffusion. Let's go through the question together. We are told that in an experiment, a drop of black ink is introduced at the bottom of a container filled with water. It is observed that the water gradually turns black. State the effect on the observation when the experiment is carried out using water at a lower temperature. And of course, these are about factors that affect the rate of diffusion in liquids, and one of them is temperature. So when we carry out that experiment at a lower temperature, the rate of diffusion, of course, reduces because the speed of molecules is low. So you could say something like this: it will take longer for the water to turn black, or a decrease in temperature reduces the rate of diffusion because the speed of particles is reduced. This word here is reduced. So you can read about the other sections in the particulate nature of matter. There are so many things you can be able to talk about there. The kinetic theory, the smoke cell experiment, Brownian motion, and so forth. Let's go to question 7, which is on Hooke's law. Hooke's law. We are given two springs which are identical and they are arranged in parallel as shown, with a mass of, a weight of 50 newtons suspended between them. When the same weight is supported by one of the springs, it produces an extension of 1 centimeter. So that information, that when 50 newtons is suspended on one spring, it produces an extension of 1 centimeter, allows us to calculate the spring constant for one spring. And then two such springs are arranged in parallel. A quicker way of knowing this is, if one of the springs has got the spring constant K and two of them are in parallel, the spring constant of that spring system will be double the spring constant of one of them. So it will be 2K. If it is three of them in parallel, the spring constant of the system will be 3K. But if they are arranged in series, the spring constant of two springs arranged in a series will be K over 2, or half K. If it's 3, it will be K over 3. This is what I'm talking about because it is part of the short notes. However, in fact, I've already worked it out here. So I worked out the spring constant of one of the springs, which is force over the extension. I got 5,000 newtons per meter. And then when I have two of them arranged in a series, then I just multiply the spring constant of one of them by 2. And this is the case. You can be able to show that if they are in series, then the spring constant will be half of this value. That is what I want to show you right now. So this is the situation that we have here. We've got a single spring and its spring constant is K. If we have two such springs arranged in parallel, like that. The value of the spring constant here will be 2K. If it is 3, we're going to have 3K. If it is n springs, the value of the spring constant of that system will be how many they are times the value of the spring constant of one of them. That is when they are arranged in parallel. How about when they are arranged in series, such that you have the first one here, then you have the second one here. If you have two of them in series, the value of the spring constant of that system will be the spring constant of one of them divided by 2, because they are two springs. If they are 3, it will be K divided by 3. If they are 4, it is K divided by 4. If they are n, then KT is going to be equal to K divided by how many they are. So it is the opposite of each other. But there is another system whereby you've got a combination of series and parallel. Here, it is not very easy to get a straightforward answer or a straightforward conclusion. Of course, you can be able to show that this is the case and this is the case using calculations. So here, you've got to go through the calculations. For example, if we had 3 such springs and this one was still 50 newtons, we have to work it step by step, one part at a time. For example, this 50 newtons, this first spring supports 50 newtons all by itself. So the amount of extension it produces is 1 centimeter. But when two of them support the 50 newtons together, each one of them will support 25 newtons. So it means that if 50 newtons produces an extension of 1 centimeter in the spring, then 25 newtons will produce an extension of 0.5 centimeters in this one, and in this one also 0.5 centimeters. Total extension for the parallel connection, is equal to the extension of just one of them. But total extension for the series connection is equal to the extension of the first part plus the extension of the second part. So the total extension here, E total, will be equal to 1 plus 1 of these, where we are going to get 1.5 centimeters. Having got 1.5 centimeters, then the spring constant for that system will be equal to the total force which the system supports divided by the extension, 0.015 meters, which is this one. That's why I said for you to get the spring constant for this combination for a series parallel connection of spring, it's not straightforward like you would have here or here. You've got to work it out in steps like that. So that is what we have as far as that question on Hooke's law is concerned. Let's go to the other question, question number 9, which is on thermal expansion, and it is on the anomalous expansion of water, where we are told that in an experiment, sketch a graph of density against the temperature for water between 0 and 10 degrees Celsius. This is water, so we are expected to recall. Remember, in physics, there are those factors which you're supposed to recall, like laws, important concepts, principles, general methods of working out a certain physical quantity. You're supposed to recall those parts. But there are others which require you to write down the answer or to work out the answer in real time during the examination period. This is one of them that requires you to recall. I require you to recall that something very strange happens with water at 4 degrees Celsius. At 4 degrees Celsius, water has got the highest density. because it's got the least volume. So we expect this kind of situation. We expect this kind of graph like that. And then you indicate that here where we've got maximum density, it's at 4 degrees Celsius. At 0 degrees Celsius, we've got density which is lower than 1. That is why ice floats on water, because its density is slightly less than 1. So if this question was very strict, you would be able to show this one being 1. Then at 4, the density of water is greater than 1. But at normal room temperature like 10 degrees Celsius, 20 degrees Celsius, it comes back to 1. But at 0 degrees Celsius, the density is lower than 1. At 4 degrees Celsius, the density is more than 1. That is why at 4 degrees Celsius, water at 4 degrees Celsius, it's found at the very bottom of a pond because it's got the highest density. But at room temperature, water has got a density of 1 gram per centimeters cubed. This is what is expected in this question here. So you can put it away and we go to question number 9. And remember, I'm just showing you the specific answers to certain questions. It's up to you now to go to those topics and try to look at those other concepts where possible. Let's look at question number 10, which is on equilibrium and center of gravity. We are supposed to state the reason why a student climbing a hill tends to bend or lean forward. Or what makes it possible for us to be able to move on a horizontal ground, for example. It's because when you lean forward, the vertical line from your center of gravity falls in front of you, moves outside the base support, which is your feet. When it falls in front of you, you become unstable. You tend to fall forward. So you tend to take a step in order to bring it back to be within the base support. And that way, because you're always trying to catch up with the position of the center of gravity, you get to move. You get to move. It is the same thing here. So the student leans forward to keep the position of the COG outside the base support and always ahead. The resultant moment due to the weight is what prompts the student to take a step in an attempt to restore equilibrium. So it's just as simple as that. Study other aspects in the same area to see what can come out of it. Let's look at question number 9, which is on quantity of heat. This is the cooling curve of a substance which has melted. Figure 6 shows a graph of temperature against time for a pure molten substance undergoing cooling, such as wax. If you heat it and when it is cooling, when it is solidifying, which is this section here, the temperature does not change, although it is losing heat to the surrounding. So the question comes in, why is it that the temperature does not fall to signify the loss of heat to the surrounding? It is because during change of state, when a substance is solidifying, it gives out latent heat of fusion. It gives out latent heat of fusion, or it produces heat which comes from latent heat. So that heat which is given out by the substance replaces the heat which is lost by the substance to the surrounding, and therefore the temperature does not fall. So to explain that, I've given you some points there which you can write down later on. The substance is solidifying, that is changing from liquid to solid. Latent heat of fusion that is given out compensates, that is given out by the substance compensates or replaces the heat which is lost to the surrounding. Hence, there is no temperature drop during the cooling process. Let's go to question number 12, which is on turning effect of a force. This is a very common question, and when you read it through, you're told that figure 7 shows a uniform rod. See this fact here, uniform rod AB. You're told that it is uniform so that you can know that at its geometrical center, you know, you divide 2 meters by 2 to get 1 meter from either end. That's where you find the center of gravity of that rod, and you must be able to show it. What is center of gravity? Is the point through which its weight acts. How is the weight of an object related to its mass? W is equals to mg, and that is where the mass of the object is given here, so that you can be able to locate that point and be able to put that point for a uniform rod. Remember, this one only happens for a uniform rod. We will see another question in section B whereby the object is not uniform. Balanced horizontally by a string attached 0.1 meters from end B. Determine the tension in the string. Take G to be that much. This is a very common question. I want to explain certain points first, and the point I want to explain is this. So the first thing we have been told is that this rod is uniform. Remember, if it's uniform, you divide that length by 2 in order to get this specific point, because you know how far it is from there. You know that this is the center of gravity of the rod, and that is where its weight acts, mg. You're told that it is pivoted here, and there is no, the string is at the very end, so it's not. Oh yes, it's somewhere around here. This is 0.1 meters, and because it's 2 meters, this will be 1 meter. That means that this is 0.9 meters, because this must be 1 meter. Then this one is the other 1 meter. Oh, sorry for that crooked line. This is 1 meter. And here we are told that, let me see, this is 0.5. So this is 0.5. And this is 1 meter. That means that this is another 0.5. So we want to determine what? We want to determine the tension in the string. Very easy, because the tension the string is pulling the object that way using that force, which is the tension in the string. So the best point to take moment about is this point. Why is it the best point? It's because if we were to show forces which are acting on this system, we will see another force. I did not draw this section carefully, because it's supposed to reach somewhere around here. That one there. There is another force here, which is actually reaction, starting from the peg, pointing upwards like that, reaction that comes into play. So how many forces are acting on this meter rule? 3 of them. Its own weight, reaction, and this tension. If I were to take moment about this particular point, I'll have to use a reaction and the tension. If I take this moment about this point, I'll have to use weight and the tension. If I take moment about this point, I'll have to use weight and the reaction. So which one is easier? It is based on the forces which have been given. You see, it's easy to work out the weight of the object because it's equal to its mass, which is 1 kilogram times 10 Newton per kilogram. And its weight is actually 10 newtons. So I know that I'm required to work out T. So it will not be logical for me to take moment about this point, because it will eliminate the force which I'm required to calculate. Remember, when you take moment about a point, the forces whose lines of action pass through that point. Let me repeat that because it's very important. When we take moment about a point, the forces whose lines of action pass through that point automatically get eliminated. That is why I would choose to take moment about this point, because it eliminates R, because I do not know it and I do not need it. So taking moment about R, I'm going to say that clockwise moments about that point, which is given by the weight, which is 10 newtons, times how far it is from that point, which is 0.5, is equals to the anti-clockwise moment, which is due to T times how far T is from this point. And you can see it is 0.5 times 0.9, which is 1.4. A few points to note. When you take moment about a point, all distances must be measured from that point. Some students may use this, wrongly use this for the tension. Number 2, moment is the product of the distance and the perpendicular, and the product of the force and the perpendicular distance. Always ensure that the force makes 90 degrees with the distance all the time. Although this one is assured, but I've seen questions where the distances and the forces, they are not perpendicular to each other. Another point to take care of is this: always identify a suitable point to take moment about, and be ready to tell the examiner, take moment about this point, and then down there you write clockwise moments equals to anti-clockwise moments, as we see in this mark scheme here. So that's it. And even on the diagram that you are given on the question paper, do not hesitate to draw or to put more information on it. There is no problem, even if you were to put extra information. And that is what I did. I had to show these distances here, although they are not shown. I have to show the position of the weight. I have to show the tension there, so that should you even make a mistake here, the examiner could be able to see where you made the mistake, and you can get away with something like that because it was not intentional. So study this particular section. I've already explained how I got 3.57 newtons. Just confirm that that is the particular answer. Question 13 is on heat transfer. Heat transfer. So let's see what we are told. We're told that figure 8 shows two pieces of ice, A and B, trapped using a wire gauze in a large beaker containing water. Heat is supplied at the center of the base of the beaker as shown. State the reason why B melted earlier than A. B melted earlier than A. Why is that? It's because when this water is heated, it absorbs heat. The substance, the water expands, it becomes less dense and rises. Once it rises, cold air from the sides, they rush in to take that region. So that hot liquid rises like that. When it reaches the top, some of it moves to the right, some of it moves to the left. So you can see that the hot water will reach B earliest, because the distance from here going that way and then it sinks again to the bottom is much, much longer than the distance to reach B just from here. So the water at B is heated earliest, or the heat from the flame reaches water at B earliest because of convectional currents which take place here. Convectional current, that this water gets heated by convection. The heat does not travel straight from this point this way. No, it doesn't. The water must circulate, and the molecules literally carry the heat from this point to the other point by convection. And convection takes place in fluids, whereby part of the fluid, when it is heated, it expands, becomes less dense, rises, and so forth. So I've explained that one in detail here. Heat is carried from the bottom of the beaker to the top by convection. The path followed by hot water is longer for ice at A compared to ice at point B. So that's why it reaches B earliest. Question 14 is on fluid flow. What are we told? Figure 9 shows a folded piece of paper. A stream of air is blown underneath the paper. We know that, explain where the paper collapsed. It collapsed because this air which is moving in this space is at a higher speed than the air outside. In fact, the air outside is still, but the air inside is moving. When a fluid flows or moves fast, when the speed of the fluid is increased, the pressure in the fluid is lowered. So the air pressure inside the paper is lower than the air pressure outside, which is still atmospheric. So that pressure difference produces a resultant force on the paper and it sort of squashes the paper. That's why that paper collapses. Again, the answer is given there. You can read it all by yourself. The speed of air is higher inside than outside. The high speed creates a low pressure region inside, while the air pressure outside the paper remained high. That is at atmospheric pressure. The pressure difference created a resultant force inwards. And that is what we have for section A. Let's go to section B for 55 marks, and it has how many questions? It has 5 questions. The first question is on floating and sinking. Floating and sinking. Where we are told, figure 10 shows a wooden block of volume 90 centimeters cubed floating with a third of its body submerged in water of density 1 gram per centimeters cubed. Take G to be equal to 10 Newton per kilogram. When you read that past paper and you see the units of water being given as 1 gram per centimeters cubed, that G, this G and this G do not mean the same thing. This G means grams. And of course, this is the unit for density. This G is the symbol for gravitational field strength. That is the amount of force that the gravitational field exerts on unit mass. So don't be confused by that. I'm saying that because some students may see this G and think that it's talking about the same thing. It's not. Determine the weight of the block. Now, the first thing you notice that over here, the wooden block is floating. So we must apply the law of flotation, which states that when an object is floating, the upthrust on it is equal to its own weight in air. The upthrust on it is equal to its own weight when it is in air. So it supports it. And then we have got to remember that the upthrust is equal to the weight of the fluid displaced. Then the other thing is, this object is not fully immersed. It's got a total volume of 90 centimeters cubed, and it's only a third of its volume that is underwater. A third of 90 is 30 centimeters cubed. So you should be able to get the volume of the solid under the water, or that is submerged. So when we use upthrust is equal to rho Vg, let me explain that. This is what we have. Generally, the object is like that. It floats up to that much. When we say that upthrust is equals to its weight in air, which is mg, and upthrust is equals to density of the fluid, this fluid here, times the volume of the fluid displaced, which is equals to the volume of this section, is equals to mg. This is the weight of the object. The density of the water is 1 gram per centimeters cubed, which means 1000. This volume, we have just worked it out to be 30 centimeters cubed, which is 30 by 10 raised to minus 6 meters cubed. And of course, this one is 10. This will be equal to the weight, and the weight of the object is 0.3 newtons. So to work out that first part is not difficult. It's only two concepts that are required there. Number one, you must realize the object is floating. If it floats, then the upthrust on it is equal to its weight in air. And that is what I'm using. Then for you to get the upthrust, remember that this is not equal to the total volume of the object. It is equal to the volume of the object which is submerged, which is equal to the volume of the fluid displaced. Because the volume of the fluid displaced will be equal to the volume of the object, of that part of the object which is under or which is in the fluid. The other part is about the weight of the metal block that can be placed onto the block so that its top surface of the wooden block is on the same level as the water surface. That means how much of a metal block, this metal block that we must put here, so that it continues to sink until the level of the water is just at that point. That means that the weight of the block, that weight of the block must be equal to the extra upthrust. Extra upthrust. This is extra upthrust is equal to, of course, rho Vg. This V is the volume, is the extra volume which must be submerged, which is this one, 60. And of course, we can follow the same method of substituting there. So just explained that concept, and when we check the answer, now first of all, there is this other section here. Figure 11 shows a solid metal suspended in oil using a thread. Other than upthrust, list two other forces acting on the sphere: the weight of the sphere and the tension in the string. Of course, show the direction. It was not asked for, but you should be able to show that the tension points upwards, weight acts downwards. The oil is carefully gradually drawn from the beaker. State the effect on each of the forces. The weight will remain the same, but the tension is going to increase. So that is how we would work out that part. We got this one to be 0.3 and this one is 0.6. And of course, the forces are tension, the weight, tension and weight are the two forces. Weight is not affected, tension increases as the water is drawn out. Why does it increase? Let's look at the explanation to that. In fact, you can be able to get the explanation from here. You see, this object at any one time is in equilibrium. So tension plus the weight, tension plus the upthrust is equal to the weight. As you draw out the water, this upthrust is going to reduce because the volume of the liquid displaced is going to decrease. And for us to maintain that equilibrium, the force which must increase must be the tension, because nothing happens to the weight of the object. The weight of the object in air remains the same because it has not moved from one point where it has a different value of gravitational field strength. So the weight remains constant because its position has not changed. And remember, The reason I'm bringing in that, it may appear to be complicated, but it's not. Do you remember the difference between mass and weight? One of them is that weight changes from place to place, but here I'm saying that the weight is constant. So the weight is constant because the position, it has not moved to a place where the value of the gravitational field strength is different. That is why the weight remains constant. And that is how you would answer that question number 15. Let's go to the question on quantity of heat. Quantity of heat. Define the term specific latent heat of fusion. This will be the heat required to change unit mass of the substance from solid state to liquid state at constant temperature. Those are some of the definitions, physical quantities that you must recall. B. Ice of mass 5 grams at a temperature, let me move it to a suitable point where I want to see this question as I answer the various parts before I show you what the actual answer is. What do we have here? We have ice. A cube of ice, 5 grams at minus 10 degrees Celsius. When it is put in water, it's going to melt, but it doesn't melt until it reaches melting point. So here we are still going to have 5 grams of ice at 0 degrees Celsius. So it absorbs a certain amount of heat, which is equals to mass of ice times specific capacity of ice times change in temperature of ice. Because it has absorbed heat from water. Then after that, the water it absorbs more heat, which makes it to melt and forms water, 5 grams of water at 0 degrees Celsius, because the amount of heat it absorbed was latent heat. And then that water which is formed, its temperature rises from 0 degrees Celsius all the way to 40 degrees Celsius. So it absorbs more heat. Here, the change in temperature is 40. The change in temperature here is 10. But the specific heat capacity here is a specific heat capacity of water. But here it is a specific heat capacity of ice. Remember that. What happens to the water from which all this heat is obtained? The water was at a temperature of, I think, 100 degrees Celsius. Immersed in 10 grams of hot water at 100 degrees Celsius. This water cools all the way to 40 degrees Celsius. That's what happens. The heat that it loses is the heat which is absorbed by the ice in order for the ice to undergo all this process. So this question breaks it down for you. For example, we are asked, calculate the heat lost by the hot water. You're going to get Q is equals to mass of the hot water, which is this one, 10.5 grams, convert it into kilograms times specific capacity of water times the change in temperature of the water, which is from 100 to 40, which gives you 60 degrees Celsius. Next, heat gained by ice from minus 10 to 0, mass of ice, which is 5 grams, convert it into kilograms, specific capacity of ice, which is 2100, change in temperature is 10. Next is the heat required to melt the ice in terms of LF, and it is here. The mass of the ice, which is 0.005 times LF. That is what they wanted you to write down. The heat gained by the melted ice. You see now the ice has melted to form water. The heat which is gained here is mass of the ice, which is 0.005 kg. Specific heat capacity of water, because now it's no longer ice, now it is water. So the specific heat capacity of ice and water is different. So you're going to use the specific heat capacity of water. And then the change in temperature is just 40. Calculate that. And then finally, the last part there is the specific latent heat of fusion of ice. So you're going to realize that all this quantity of heat which is gained here is obtained from here. So you equate this to this plus this plus this. This one, you can be able to get its value direct. Here you got the value in terms of LF, and here you got its value direct. Here you also got a direct value. So use that concept in order to get the answer to that part. Let me just arrange this one properly so that I'm able to access what I want. So let's see the answers, and that is exactly what I was talking about. So first of all is the definition of specific latent heat of fusion of the substance. Remember to state that this occurs at constant temperature. But B, heat lost by hot water, we have already worked out that, we got 2646 joules. Heat gained by ice is this much. Heat gained by melted ice is that much, and then you equate heat required to melt the ice and get the value of LF to be 340,200 joules per kilogram. And that is how you would answer that part. Let's quickly go to question 17, which is on pressure and turning effect of a force. And we have this system here which combines turning effect with hydraulic system. Now, we are told that the figure shows a hydraulic lift system. The radius of the small piston is this much, while the radius of the large piston is this much. The small piston is operated using a lever. A force of 100 newtons is applied to the lever, this one here. And then you're told, determine the pressure exerted by the smaller piston. The pressure exerted by the smaller piston. For you to calculate pressure, you need the force and you need the area. It's easy to calculate this area using pi r squared because you've already got the r. And remember to convert the centimeters into meters. But the force exerted here is not this. Why? We have a lever system which multiplies that force several times. In fact, it multiplies this force like how many times? Like, I think 5 times. How do I know it's 5 times? Do you see the effort arm, which is 2 meters, compared to the load arm, which is 0.4? How many times does 0.4 go into 2 meters? 5 times. So you can be able to know that the force exerted here is 500 newtons. It is 5 times this. However, you can comfortably work that one out using the principle of moment. You will take moment about the hinge. So 100 newtons times the whole of this distance, which is 2, is equal to this force times this distance. And again, you're going to get this force to be 500 newtons. Now the area, I've already said it is pi r squared. So to get this pressure, it's very easy. It is force over area. 500 newtons divided by that area. Next, we want the load that can be lifted. This way now we use the hydraulic system. F1 over A1, which is of course the pressure in the liquid, and we already know it. So you can say that pressure in the liquid is equals to F2 over A2. Therefore, this pressure, which we already know from part A, is equal to the load divided by this area, which we can obtain because we know the radius. And from there we can be able to get the load that can be lifted. The good thing about this question is that it shows us how concepts in one topic can be combined with concepts in another topic, because most of the time we tend to treat these topics as if they are separate, but we can be given a system whereby more than two topics or more than two concepts are being applied. For example, the two topics involved here will be turning effect of a force and, of course, pressure, the hydraulic system. And of course, we are forgetting the third topic here, which is work, energy, power, and machines, because we are asked to calculate one of the physical quantities which we can use to define a machine. Mechanical advantage, which is equals to the load over the effort. Remember the load, we have it. The effort this time is not here, but this one here. So that's how we calculate it. Quickly, let's look at the system we have, and I've shown you that force that we require there, how we use moments to get the force. We calculate the area, we calculate the pressure, and then the other part is this one here, force equals to pressure times area. We got in the load, and then the mechanical advantage is load over the effort. This divided by that, which gives us 32. So that question combines three topics. Very good question. I will propose that you study that question once again. Question number 18 is on linear motion and Newton's laws of motion. Let's see what it entails. A bus moving with an initial speed or velocity 20 meters per second, that is u, decelerates uniformly at 2 meters per second squared. So the acceleration is -2. Where does the minus come in? It's because of this mention of the word deceleration. Let me show you how we get that. Now, the next part is to sketch a velocity time graph for the motion of the bus up to the time it stopped. So it starts with a velocity of 20, ends up with a velocity of 0, and it's uniform deceleration, so it's a straight line that is sloping like that. Use the graph to determine the distance covered by the bus before stopping. Of course, one of the concepts is that the area under a velocity time graph will give you the displacement. This time it's the magnitude of the displacement which gives you distance. The last question, or the last part, that is part B, we've got a car of mass 1000 kg traveling at a constant velocity of 40 meters per second, collides with a stationary metal block of mass 800 kilograms. The impact takes 3 seconds before the two move together. Determine the impulsive force. So, for you to determine the impulsive force, which comes from impulse, you must remember that impulse is equals to change in momentum. So we are going to say that impulse on the car is equal to change in momentum of the car, or impulse on the metal block. Impulse on the metal block is equals to change in momentum of the metal block. Either way, we can get the impulsive force, because since we are using Newton's third law, we find that the force that the car exerts on the metal block is equal to the force the metal block exerts on the car. So working out the force either using the car or the metal block will give us the same answer. But for us to be able to get the change in momentum of the car, we must get its final velocity. So we must get the combined velocity. And that is where the principle of conservation of momentum comes in. So we must look at the momentum of the system before collision is equals to momentum of the system after collision, so that since these bodies coalesce, it will be easier to work out the common velocity. And then using that, we can use the concept of impulse is equals to change in momentum. And let me just look at the answers here. Number one, the time that we were asked to calculate, which is t is equals to v over u over a, is 10 seconds. So this is 10 seconds. It helps us to get this velocity time graph. And working out this area will give us the displacement, which is 100 meters. The idea of conservation of momentum helps us to get the common velocity, which is 22.2 meters per second. So the initial velocity of the car was 40 meters per second. The final velocity is 22 meters per second, moving in the same direction. And therefore, we are able to get the change in momentum of the car, which is this minus that. Of course, using that is going to give us an impulsive force with a negative sign. The negative sign, of course, shows that the force is in the opposite direction to the direction of movement of the car. Study how I have done that, and let me know in the comments below where you're having challenges, because that one would also be an opportunity for you to be able to dig deeper and see where and be able to understand that question much better. Last question. At last, we are in question number 19. I've gone through that paper very fast because I want to keep the time to be a little bit shorter. However, question number 19. A, state the conditions necessary for a body to be in equilibrium. There are two conditions. One of them is that the resultant force on the system must be 0. And number 2 is that the resultant moment must also be 0. Those are the two conditions that must be fulfilled for a system of forces to be in equilibrium. And then in part B, this question actually had an error. The error was they forgot to give the mass of this object. So they worked out the answers with the weight of the object. So in my case, I've given you a value of 15 kilograms to help you to work out this question. It is on moments and center of gravity. Unlike the other question where in section A, there was a question on equilibrium and center of gravity, where the system was, let me look at this, not that one. There was another one where turning effect of a force. Yes, here. In this one, we were told that this rod was uniform. So it's possible to get its center of gravity. But in this other question here in section B, it is a non-uniform log of wood, AB. So it's not possible to get the position of its center of gravity. We have got to calculate it. For us to be able to do that, I found it necessary to include the mass of the log so that you can get its weight. I just chose any random number here. We are told that the log is held horizontally by applying forces of 80 newtons and 120 newtons. It's a matter of showing the forces, how the forces are acting on the system, and then deciding on the point about which you take moments. So this is what I would suggest. You go through this topic, center of gravity and equilibrium, this one here. Review concepts on the turning effect of a force, and then work out the various parts of that question, and then click here to see the answer. Of course, you're going to download this package. Once you have downloaded the package, I've already shown you how to go about opening it up so that it reveals to you exactly what I have here without any problem, and you can start navigating through one question to the next. So I have left out that one question for you just to make sure that you download this and be able to check through and test your knowledge of equilibrium and center of gravity. Otherwise, I want to thank you for being patient for this very long video. I hope it has been of benefit to you. And if it has benefited you, don't hesitate to share it with your friends. because a candle does not lose its own light by lighting another. It doesn't. So share it with your friends. In any case, when you share it with your friends, they might be able to see something which you never saw. And therefore, through that discussion, you get to gain something. Another thing that I'd like you to do, if you're not yet a member of my channel, go right ahead and subscribe. Look at the many videos that I have in that channel. They are all on physics, and I'm sure you can be able to gain a lot by looking at the various videos. Otherwise, in the next video, I'm going to look at physics paper 2, or a complete topic in our KCSE syllabus. Bye bye for now.